Hi guys, see, I wanted to teach you a few more things related to the application of Gauss's law. In fact, Gauss's law has a larger application to understand the various situations of charge distribution and the associated electric field. So, mostly in any case, Gauss's law, Gauss's law, Gauss's law is used to determine electric field around a given charge distribution. So this happens to be a very useful path because of the shape, the freedom of the shape of Gaussian surface we can assume. It has no particular shape, there is no requirement on it, it only needs to be a closed Gaussian surface. So it can be any shape, it can be a shape such as this, it can be a perfect sphere, it can be a closed cuboid, so it can be anything, or it can even just be a half cylinder. No issues on whatever the shape is. So the freedom of choice of Gaussian surface is a good thing, but in fact, along with the freedom of choice, freedom to choose the Gaussian surface as shape, there is one more requirement that makes Gauss's law a very useful applicable law. It's very clear from its equation form. If you remember, see, the Gauss's law has two major forms, the differential form and the integral form. I'm going to give you the integral form because you have learned the summation form of Gauss's law. So converting from the summation law to Gauss's law is much easier than going to the differential form. So the Gauss's law in its integral form looks like this. This symbol stands for integral of this quantity, sum of this quantity. That quantity contains the dot product of electric field to ds. Instead of here, ds is in fact the tiny area vector, the differential area vector on the Gaussian surface, and electric field through that Gaussian surface is the vector E. So doing a dot product on this tiny elemental area, we sum over all the other tiny such fluxes. This individual product is called a differential flux, and as you go ahead to sum over all these tiny differential fluxes, you will get the total flux over the prescribed surface. If it is a closed surface, then we will put a loop integral form, and there will be an indication over which the indication of the type of surface over which this integral is being done. So you are, in fact, you are just adding this much quantity over the entire surface. That is what is happening here. So let me just get rid of the additional things that I have drawn. Let S stay there. The answer to this question would be nothing but, as Gauss has found it, it's the net enclosed charge divided by the epsilon, the permittivity of the media. If the medium in which this measurement is being done is vacuum, then we will be using epsilon naught. So from this equation, it is very clear that the dot product integral is mathematically convenient to evaluate when this dot product, let me just write the magnitudes alone, E ds, this is what the expanded form of the dot product look like. This becomes easy when the value of E is the same on every point on the surface. So that is one point. This integral is easy to evaluate, as if E has same value all over the surface, all over the given surface. So S represents the surface. In that case, we need to just pull out E from the integral and do the following integral. This further can be simplified by knowing relationship between the area and the angle using the coordinate system, by transforming into a convenient coordinate system which has ds described in terms of theta and doing the corresponding integral. So that is not considered here because it's a bit more complicated one and requires advanced level calculus. So let us not think of that. So this one is the major, the main point was this was the major point. E should have same value all over the surface. Next convenience that we consider is when the cos theta, when you do the E dot ds thing, you come up with the magnitude of E. Oh, I no more need that arrow. E ds times cos theta. This product becomes easy when this cos theta part becomes 1, becomes unity, and that happens only when E and ds, let us restore their vectors forms, when E and E are parallel or anti-parallel. So if it is anti-parallel, the value of cos theta should be -1, anti-parallel. In that case, the integral entirely becomes just E ds, and to evaluate this is nothing but a right hand job if you are good enough in calculus, doing calculus, especially advanced level. So further moving on, provided if you have this parallel anti-parallel situation, let me say if your vector E is parallel or anti-parallel, I guess is something like this. If it's parallel or anti-parallel, it could get rid of this cos theta part. Then we are left over is with this E thing. If the magnitude of E is independent of the direction and only depends on the distance r, if E is independent of the location, the location where you look at, that means if it is independent of theta, phi, parts, these are just coordinates, these are spherical polar coordinates. If E is independent of theta and phi and alone depends on r, and we could go ahead with surfaces such as a spherical one, thus making it look like this. So we can assume a surface on which the value of E becomes constant and independent of where you look at, then we could evaluate the integral very easily. So even in that case, the integral shortened down to this much. Now all you need is to evaluate the sum of all the areas, tiny areas on the surface. If you have a big surface, big closed surface, and you have tiny areas on them, and you go on ahead to sum all those areas, you would end up with the entire surface area, value of the entire surface area, and where E was there already, thus making it an easy task to find E from this expression. All you have to do then is to just separate the final value of the integral, which was equated to the q by epsilon 0 thing using the Gauss's law. All you have to do is to write E equals q times epsilon 0 s in the denominator. So this is what will be used in evaluating, and mostly those will be simple cases where all these kinds of symmetry exist. One such situation is when the plane, when the charge distribution is an infinitely large, uniformly charged plane, uniformly charged infinite plane. And if I remember, I had indicated how this plane looks. It's just a flat surface on which there are charges, maybe positive or negative, which are uniformly distributed, and it extends forever in all possible directions. So it's a plane, it goes on ahead to infinity in all possible directions, there to there to there and here, wherever possible it's going on to go infinitely large. But the charge distribution is assumed to be uniform, which means whenever you go on ahead to pick a small area here on this entire surface or here or even somewhere very far apart, the amount of charge contained within this small area of equal magnitudes will be equal, it would be same. If that is the case, then we can define the surface charge density of such a plane sheet. So what is that? It is just the area, charge per unit charge found in unit area of the plane surface, and its unit is coulomb per meter square. So let sigma be the charge distribution, the surface charge density of the given plane sheet. Now let me just stand this plane sheet up. Let me just stand this plane sheet up. Actually, these are not the bounds of this plane sheet. This is just a tiny region, and as you know, these walls do not end here, but they extend up to infinity in every directions, up or down, left or right. Let us assume that our given sheet has only positive charges in them, so it is uniformly distributed all over and contains plus charges everywhere and has a uniform distribution, so has got a very nice surface charge density. So this would take like an entire year to build up this drawing, so I will stop here. Now the question comes, when you pick a point right in front of the sheet, let me use a different color so that you just get a grasp. Suppose you are standing here on the surface and you get a chance to fly away from the surface to a certain distance. Say I call this distance r, yeah, I could call it r, and at this point I can see the entire charge distribution from this point. I'll call this point M. My next question is there an electric field at the point M? Of course there is, because you could see a charge distribution right behind you, and that is also infinite. So why should you assume that there is no electric field at the point M due to this plane of sheet? All right, so it's a very large surface, so the resultant electric field, the net electric field, should be in what direction? Let us evaluate this. Right at the bottom, imagine a tiny area, a very small area. Say I can call it maybe dA, since D because it's a very small one, and A for area. Okay, let this red circle be a very small area of magnitude dA. If sigma was the charge density, then what would be the amount of charge in this dA elemental area? And that charge would be some small amount, obviously some dq, which would be equal to nothing but sigma times dA. So that much charge resides there, and since dA is a differential, we could go on ahead to make it as small as possible, such that from point M this area looks like a point charge. So it is as small as that. Then the direction of the electric field at this point would be exactly along the line joining, but since it's positive, the electric field at M would be, let me use a different color, the electric field would be in that direction, because that indicates the line joining, the direction of the line joining the area, this area, and the point M. So that's just only one particular case. What about the rest of the plane? Okay, I'm not going any further, but let me just pick a small area here at a certain distance away from, in the up direction at a certain distance away from this initial dA area, and call it dA1. You can go down and pick another area at a similar distance and call it dA2. You can move sidewards at the same distance and get another area dA3, and you can move this way to get another area having a magnitude dA4. You can do that in all possible outward direction, giving you a strip of area which are all at the same distance away from this initial area. Now imagine that this circle, this shaded circle or this strip can decrease in size, converging towards our red zone, or it can be such that it expands outward. But at any moment it has a lot of dAs on it. So there is a dA here, dA1 there, there can be another dA here, there could be another here, another one here. So on and on and on, you can go ahead to define a lot of tiny areas, small, extremely small ones that contain certain amount of charge dq in M. So due to individual tiny areas, the electric field would be along the line joining them. So for in the case of dA1, the line joining is this purple one, and the electric field would be outward since it is a positive charge, and it will be in this direction. Due to dA2, or in this case it is dA3, I guess, I don't know exactly, I don't remember exactly, it goes to be like this. So that was just on a single line. Now it was this line's electric field that gave you this. Now you can go on ahead to define the electric field on this line. Which areas to come in that line? dA4 and dA3. Due to them, since they themselves are in a line where perpendicular to the first line, which contain dA1 and dA2, their electric fields will also be in a plane perpendicular to the first three ones. So if you kind of rotate this line a bit differently, you will again have another set, and you can go on ahead to define another circle, another line, and you can again have another set of lines, areas, corresponding to them there would be electric fields that look like, I mean it's getting complicated, I know. Suppose this was our point, and if I am drawing it slightly towards you, then it would look like this. If I am drawing it towards you, actually these arrows are bent forward and are facing you. So it's basically like a cone that has a head at M, has the pointed vertex at M. So it's a cone in fact, and also there is this. So these are electric fields for a given strip, for a given strip, okay, this was our strip, we have drawn it in blue and now we have covered it with purple, and that was a strip, and that was the case for. Now where is the resultant of all the electric fields on this cone surface? See, let me just take two cases. Let me just take two cases first. Let me use yellow. Let these two be the first ones. You know, since they are equally separated and have equal magnitudes, their resultant would pass through exactly the center of the cone, the axis of the cone. So resultant of these two is through the center. Now any two electric fields opposite to each other would add up to give a resultant electric field that would be through the center of the cone, that would represent the center of the cone. Now only thing that's going to happen as we add more and more of these small surface arrows is that this arrow direction is going to remain same, but its strength keeps increasing because you add more and more. So this was the case of only one strip source. You can go ahead and define another strip, another strip, another strip. So you are basically spanning the entire surface, and for each strip there will be a separate cone that has the same vertex M. So due to each cone, the resultant will pass through exactly the center, which means looking at this gives a following situation. There was a sheet, you had this sheet, there were so many charges right exactly atop of a certain point. I forgot to name this point. Let me name it N. The point on the surface be N, and let me locate the point M, which was at a certain height R from the point N, and where N was the base. For every strip around this N, you found that there was a net electric field which pointed always vertically outwards. So this is what happens. Now if this was a limited sheet, if this was a sheet limited by this much region, then the electric field could only point exactly like this, I mean perpendicular to the plane of the surface. That is only possible in a limited case if the point N was exactly at the geometric center of the plane. But for an infinitely long plane, for an infinitely large plane, this is not the case. You assume one N here and call it N1. You assume another point N2 on the sheet somewhere here. In each case, you go to a certain height, and at that point the electric field would always be pointing straight outwards, perpendicular to the surface or parallel to the surface area vector. Why does this happen? This happens because since this was an infinite plane, you be here or here. Suppose you were here at N1, you could only see infinite expanse towards that direction, this direction, here or anywhere on the plane would always be infinitely far away. The edges of the plane would be infinitely far away. So it is in fact the center of that particular plane. But when you come to N2, which is slightly displaced away from you, even in this case the sheet is infinite, which means all the borders are also equidistant away from this point N2. So assuming N2 to be the center of this plane sheet is also valid, because if the borders are equally distant from both n1 and n2, then both n1 and n2 can be the center of that plane. So if that is the case, due to that symmetry, the electric field must always be pointed perpendicular to the plane of the sheet itself. This means wherever you go for an infinite sheet, the electric field points perpendicularly outwards, like that. So we have not assumed anything else. We do not know whether the value of E depends on R or not. We have not assumed. Only what we have found out is that, let me use a different color. Only thing that we found was that the electric field points perpendicular right above the plane sheet at anywhere, here, there, anywhere, the electric field always points in that direction, which means all the electric field vectors are parallel to each other in this infinite case. Now we know the direction of the electric field. How would you find the electric field's magnitude? Since it's an infinitely large sheet, imagining a sphere that could contain the whole sheet, a closed surface that would contain the whole sheet, would be absurd, because that would make things only complicated. It's already an infinitely long sheet, and how could you cover it with a closed sheet of finite dimensions? That is also impossible. I mean, if it is possible or not is another question which I leave to advanced mathematician to answer. But still, in our case, we do not need to worry too much into these kinds of things. Whether it be infinite or finite, we can always consider a tiny portion of the sheet. We can always consider a tiny portion of the sheet. So let this be the tiny portion and let its area be A. Now this was this infinitely vast sheet, but we only focus on this small area. See, in fact, there was no need for me to imagine a square shape, or I could have just used a circular area or even an irregular area, but this freedom made me choose a square area. That's all. It could have been a circle, or it could have been just an irregular shape. It could have been a rectangular area or some semicircle like that. Anything, no problem in that. So to make the cases convenient, I am using a square shape. That's all. Every other area, imagining every other area below is equally valid. Okay, so just don't hesitate in thinking otherwise. Now why did I do this? Now this much area contains certain amount of charge, right? This much area alone contains certain amount of charge, and what would be that charge? Since we know that this sigma was the surface charge density of this sheet, knowing the area, we can calculate the charge, which is nothing but sigma times A would give you the charge on that small area. It's going to be sigma A. Okay. Now let me take that piece out. This was the piece, right? Now this piece, how do I cover this entire piece inside an imaginary Gaussian surface? Imaginary Gaussian surface, I could just use an irregular shape. Now it's inside, except for there is a small gap. Now it's inside a shape, but using this will not make the calculations convenient anymore, because every point on this surface is actually not at equal distance from the tiny portion itself. See, as you can see, this region is much closer as compared to this part on the surface, which means it's, if the distances are varying, then electric field, which at least should depend on R, will also vary. So if E varies, then integrating and taking E out as a common factor would become impossible. So what else suggestions? Not even a sphere. You cannot even imagine, even imagining a sphere is possible, but there is no use. Just let the sheet be A. Now imagine a sphere. Even in this case, the complication comes, see, this tiny portion is much closer to this point, say P, than this portion of the sheet. So this is far, this is close, which means this thing would generate different values of E on the surface. Also, not only that is the problem, there is issues with finding the flux, because there is this dot product thing I told you earlier. Here the area, surface area would be this way, and the electric field due to the entire sheet was somewhere like this. So there is actually some angle, and that angle would change as you go down and up and down and up. So it's making things more and more complicated. So I don't want a spherical area either. Then what else do we have? I can imagine, since this is a square, I can imagine, let me redraw a little bit better version. If this was your area A carrying that sigma A charge, I could imagine, let me draw the imaginary surface using some other color. I could assume a cuboid, not a cuboid, it's a cuboid. I could imagine that a surface of this kind. So now this is a closed cuboid, and also A is such that it is placed exactly at the center. So which means it is symmetrically distributed on this side as well as on this side. So just assume that the red area, which was on the plane of the sheet, charge sheet, is now at the exactly at the geometric center of the imaginary cuboid Gaussian surface. So I can call it imaginary cuboid Gaussian surface. I guess there is some international organization abbreviated in this form, ICGS, but let it be. In our context, it is imaginary closed Gaussian surface, which was our cuboidal Gaussian surface. Okay. Now everywhere on this surface, the electric field, what was the direction of electric field on every point of this surface, because it is the E dot ds has to be evaluated at the surface. Let me go on top. Let this be the point. At this point, the electric field due to the infinite plane sheet was in that direction. That was the direction, which means it is on the plane, right? It is on the plane, which is parallel to the plane. But at that tiny region, the A vector, the small area vector, is perpendicular that's an issue. Over here at that particular point, both A and E are perpendicular. If you call it an issue, I don't think that's an issue, because it's a good thing, because if two things are perpendicular, then their dot product must be, equal to 0. Because of the cos theta factor, it should be 0. So this is for every point on this side face. On the side face everywhere, here the electric field is that manner, but the area is this manner, but still perpendicular. Go on further ahead, then electric field is in the same direction because all are parallel, area is still perpendicular, again we get a 0 dot product. Underneath, go underneath electric field is in that direction, but the area is downwards, but still they are perpendicular. Over here also electric field is in that direction, but the area vector is downwards, but they are perpendicular, again 0 dot product. What about side faces? Even on side faces, like say here, I mean on this side face, okay, this point is on the side face, and here the electric field is like this, but the area is towards you, still this both are perpendicular. So anywhere on the side faces, the electric field and the dA being perpendicular to one another make the dot product vanish. So you do not need to calculate the fluxes on the side faces, you do not need to calculate the fluxes on any side faces. So where do you in fact need the dot products? The dot products are necessary only at these front faces over there, and there is one more front face, actually that could be called the back face, and it was over here. So these are the only two regions where the I vector, sorry, not the I vector, but the dA vector and the electric field vector are both parallel to one another. So since we found that there were a few cases where the dot product went 0, then getting rid of them, we are left over with is the sheet in between having the area A, and there was this front area of the imaginary surface, and we had the back side area again of the same cuboidal area. So that was it. So on the surface, the dA vector is in that direction for here, and the electric field was again parallel to the, and we had, and also from the given charge distribution, this any point has the same E value, since it is situated at an equal distance from the surface. So every electric field and corresponding fluxes evaluated would generate E dot dA, which was again since they were parallel, the product becomes EdA. So adding all these tiny fluxes, I mean flux through this much area, this much area, this much area, we end up summing flux on that area. I mean there are two sides, of course. I can call this side 1, got this side 2. On side 1, let this be for side 2, let this be for side 2. this be for side 2. For side 2, the sum of all the EDA would be, since E was constant all over the surface, I can pull that E out of the summation, and what we are left over with is summing the area of this surface. What is the area of this surface? As you can see, it is just a trace out of the charged surface itself. So summing all the tiny areas on the surface will add to give you A. So we have E times A on side 1, on side 2. What about side 1? Side 1 also has a similar situation, because on the surface dA points outward, and electric field also points outward. So both are parallel again. You have a sum over situation, and that sum over situation was like this: EDA, assuming the same thing on the other side, we end up having a value E times A on side 1. So that is the flux through two phases, and the flux through the side phases, I mean flux through this phase or the opposite phase or the phase side facing you and the below phase, all are cancelled out and their contributions are 0. They have no contributions at all. So what is the contribution because of the side phases? I can call them the third sides, all side faces. The contribution of E dot dA was 0, since at side faces E and dA's were perpendicular. So you didn't, now what is the total flux through the entire cuboidal closed surface? Now that is the next task we have. The next task is what is a total flux. The total flux through the cuboidal surface, say call it phi total, equals the contribution due to the phase 1 due to the plus contribution to the phase 2 plus all the contributions of the side faces. Due to contribution 1 it was E A, due to contribution 2 it was also again E A, but due to side phase 3 it was 0. Then the total flux is found to be 2 times E A. So that is your net flux through the closed surface. That is the value of the net flux through the closed cuboidal surface. That is the total flux through the closed cuboidal surface. According to Gauss's law, this net value is equal to Q enclosed by the closed surface divided by epsilon 0. I can call it Q enclosed. What was Q enclosed? Q enclosed was earlier found. Q enclosed is given by sigma A. Substituting this equation and this equation, we get the following. What was phi t? Phi total was 2 times E times A, where E is the electric field on each point of the surface, equals Q enclosed. Now what was Q enclosed? Q enclosed was sigma A, and according to Gauss's law, the total flux should be equal to total charge enclosed divided by epsilon 0. cancelling out similar terms from both sides of the equation, we are left over with the value of electric field equals sigma divided by 2 comes on the other side, so 2 by epsilon 0. So that is the electric field due to a plane sheet of uniformly charged, which is uniformly charged and is infinitely large. Here this equation could be analyzed and found that sigma, which is the property of the sheet itself, has a constant value, is constant. Epsilon 0 and 2 are also, epsilon 0 was the physical quantity, the permittivity, so it's a constant, 2 is a constant, so both of them are constants. So we have electric field and we have constant, so we get the following equation: electric field E equals a constant. So there is no distance or nothing on this side, all constant. We have electric field equals constant. What is the case where this happens? So where does this case occur where electric field is constant? See, it is a property of a field when it is uniform, and the field is a uniform field, a uniform one. So we have analyzed the situation in two ways. One was when we saw that the plane sheet, this infinite plane sheet, produces electric field at any point nearby around it, which is directed perpendicular to the plane itself, which means, as you can see, if all of them are perpendicular to that given plane, then they are parallel to one another. And now this sheet has got a charge density of sigma. That means at any point, say 0.1, 0.2, 0.3 or 0.4, 0.5 or any point around it, even here say call it 0.6, or here call it 0.7. See, this sheet is infinite, so it is extending way beyond all this. Okay, so at everywhere, whether it be close to the sheet or far away from the sheet, whether it be behind the sheet, mostly very close to the sheet, everywhere the value of the electric field is the same. It's sigma over 2 epsilon 0. Here again it is sigma over 2 epsilon 0. Here also sigma over 2 epsilon 0. That is the value of electric field everywhere, sigma over 2 epsilon 0. Even here it's sigma over 2 epsilon 0, which means the electric field are all parallel to one another. At every point they are parallel to one another. Also their magnitudes, their lengths, the length of the magnitude of the electric field vectors are the same. Such a field is actually called, in fact they are known as the uniform fields. So you get an idea of what uniform fields are. Uniform fields are those fields which have same value at every point in space and are parallel to each other, parallel to each other, or otherwise we could say that they point in the same direction and have the same magnitude everywhere in space. See, not only on these discrete points, even here, even here, even there is another electric field. There is another electric field here also, in between them. So everywhere there is continuously a value for electric field. So everywhere, so we can draw continuous lines, and you know what those continuous lines are. Those continuous lines are in fact the field lines. They are known as the electric field lines. So the electric field lines actually occur because, whenever there is a source, electric fields are not defined on certain discrete points, but they are defined on every point in between, and between 2 points, on every point. It's actually like a real number. There is always another real number between any two real numbers. So like, it's a continuous situation. So in a continuous situation, drawing electric field vectors is improper. It should be instead represented using a continuous line. So this is what it is. This is an electric field line. Actually, everywhere, every point on this line has a vector associated with it. Every point, every point on this line has an electric field vector, and since all the vectors are pointed in the same direction, we only need to indicate one arrow, indicate them all using one